This is some extra practice for people who want it. This was, I think this was a test a while ago. Maybe it was a practice test. There's some kind of sketchy problems on here, but it's good practice anyway. Maybe a little harder, if anything, than it needs to be. The first couple of diagrams go together. It's just giving you practice drawing a diagram with forces and net force, and applying different ways to arrive at net force and find individual forces. I've got a 1 kilogram car traveling to the right on a level surface. No engine, no one's pushing, it's slowing down. So somebody must have pushed it and it's slowing down. So it's going that way, but getting slower. Draw a free body. It's not really a free body diagram, technically. Just a diagram with forces and net force. So we've got to draw all the individual forces in the net force. So it's 1 kilogram, which means the weight is 1 kilogram times 9.8 mg, and the normal force is the same. And since it's slowing down, there's got to be some force to the left. What else would it be other than friction? It could be drag. I guess we'd call it drag, but whatever. Whether you call this friction or drag, there's some force to the left. Now, to figure out what this force is and what the net force is, I've got to use Newton's second law. So mass times acceleration. The acceleration is given in here in sort of a passive kind of way. The car's velocity is 1 meter per second slower than the second before, every second. So that means it's slowing down by 1 meter per second per second. So the acceleration is negative 1 meter per second squared. So mass times acceleration gives us negative 1 Newton for the net force. Now these two forces cancel out, so all of that net force must be contributed by this force of friction. So now I have all my forces. Second picture, this is the before, so this is the prequel to that. Before the car began to slow down, a child was pushing it rightward with a force of 3 newtons. Create another diagram showing all the individual forces and the net force acting on the car while the child was pushing. All right, well, this is not really a great question. So the teacher was thinking that people are going to figure out that there was friction before, but like I said, that could be interpreted as being drag, not friction. So this really, it would have been a good idea if it said this is a force of friction, and the force of friction is constant regardless of the speed of the car, which is kind of a property of friction but not of drag. So when we draw this, when the child is pushing it, now we can add the push, but all the other forces need to remain. So it's still the same mass, same weight, same normal force, assuming that push is horizontal. I don't know why we would assume otherwise. And it would still have its same friction. So the net force would no longer be negative 1. The net force would be 3 minus 1, which would be 2. That's the only difference. All right, number 3. On the test you're going to have, I'm not going to have you do a graph like this. The graph is worthwhile. It's good to think about. But instead of a graph, I'm going to have you do a series of diagrams, a series of pictures showing what the individual kind of like a series of these, but as an event is changing. So in this particular case, the event is a car starting from rest, driver accelerates leftward. Oh, gosh, this is all wrong. I was trying to be tricky there and I made it all backward. So for my answer, well, if it were leftward, this should all be flipped. So whatever's positive should be negative, and whatever's negative should be positive. Whatever. So I'm going to just talk about it moving to the right here as I explain my graph. So the driver accelerates rightward at the car's maximum possible rate, meaning puts the pedal to the metal. The driver reaches 50 miles per hour, sees a deer, hits the brakes, slowing to 30. He then continues with maximum acceleration until he reaches the top speed, which he maintains for 20 seconds before hitting a tree and coming to an abrupt stop. Sketch a graph of net force versus time. The system could be either the car, the driver, or both. I'm doing the car, or at least I drew pictures of the car. As I mentioned on the test, I'm going to have you do a series of diagrams. So in the beginning, at the start, the motor is engaged, and I should put the net force. The net force is going to be basically the motor in the beginning. And the only reason I didn't start at a high force is you can't just go from no force applied to a strong force. So there's got to be some sort of increase in the force. Now, as the driver accelerates, this is a positive net force. That net force is going to decrease because there's drag on the car. So as the car goes faster, the wind's going to be pushing back on it. So the net force is still going to be forward, but it's going to be smaller. It's going to be the motor force minus the force of drag. So that's why this is shrinking. It's positive net force corresponds to a curve here above the x-axis on this graph. Then we get to this moment and the driver sees a deer. Sorry, well, I've got an extra picture here. As the car speeds up more and drag increases more, the net force gets even smaller. So that's just this going down, down, down. And then at some point, the driver's going to hit the brakes. Doesn't say so, but it makes sense to let go of the gas pedal and apply the brake pedal. So now we still got drag, and now we've got brakes too, so the net force is actually backward, and it should be really big if I'm drawing the net force, because it should be this plus this. So suddenly we jump to a really negative net force. And if my paper were longer, I would make it go down farther, because I'm thinking that's going to be more abrupt than the acceleration. Most cars can stop faster than they can start. Most cars. In fact, I don't know of any cars that can start faster than they can stop. All right, so here's where the driver initially hits the brakes. The car's still moving, so there's still some drag. But as the driver continues braking, the car's going to slow down, drag's going to decrease. So we still have a backward net force or negative net force, but it's decreasing. So here's sort of maximum and then still negative until right here the driver's going to let off the brakes and engage the motor again. So the car never really stopped. We're only down to 30 miles per hour, so the drag never really went away. Oops, I guess I should make drag a little bit bigger there. Drag never went away, so now we're back in positive territory. The motor's going, the motor's stronger than drag, so we're going to have a positive net force speeding back up. And then the pedal to the metal means that drag is going to keep increasing. The motor force can't get any stronger. This is maximum motor force. The drag is just going to build up and build up and build up until the drag equals the motor force, and then the car can't go any faster. So the net force at that point is 0. That's like terminal velocity. If you're going as fast as your car can go, the forward forces and the backward forces, they're equal. You're at a constant speed until you damage your car in some way. So that would be right here. So this is the motor being stronger than drag. The motor is staying the same, but drag is increasing. Eventually drag gets to be the same as the motor, Now we're maintaining that top speed, and then we hit a tree, or driver hits a tree. Exactly how to envision this, I don't know, but I do know that the tree, at the first moment of impact, the tree isn't going to push very hard, but the more the car squishes into the tree, the harder the tree is going to push. So that tree force is going to spike. Also, in the beginning, the car is still moving, so there's still drag, and maybe the driver still has the motor going. But regardless, if I drew this right, I think that the tree would probably at this point be slowing the car down. This minus that plus that, these two are working together. We're going to have I'll draw it over here. The net force is going to be maybe this big. And then as the car squishes a little bit more and slows down a little bit more and the motor stops, the driver is incapacitated or realizes I should stop pressing the accelerator, then there's no rightward force, so the net force is now really big and to the left. Here's the net force. And then at the very end, the car has come to a stop, so there's no drag. And if the car is stopped, then the tree's not really pushing on it, and it's not pushing against the tree, and the motor's done. And all that's really left would be the car's weight and the normal force. But I've been leaving those out the whole time because they're balanced. So the net force at the very end is 0, because there really aren't any forces left acting on it, except those, which cancel. So looking at the graph, when it touches the tree, it slows down and we get a big backward force. Now, just to do the graph, you don't really have to think about the individual forces as much. You could just think about accelerations. So anytime we're in the positive region here, that's when the car is speeding up. Anytime we're in the negative region, that's when the car is slowing down. So net force is proportional to acceleration. So you could think of this as an acceleration graph. And if this were an acceleration graph, the area under the curve, this area, that would represent the positive change in velocity. And then these areas would represent the negative change in velocities. And since the car was at rest in the beginning and at rest at the end, these negative areas should be equal in area to the positive areas, if I drew it right. I'm not going to be too picky about that. 13 minutes. Guess I'll go over this, although I went over this in class. So if you need help on this, I'll just refer you to the last couple of classes. There's a link that says something about a video that you need to go to the 33-minute mark, and then I explain this. No, that's the graph. I can't remember exactly what that link is now. There is a video where I go over this as a warm-up from last year. Oh, so I'm not going to do this right now. I did it. Oh, you know what? I did this at our meet yesterday. So if you look at the meet from the class on January 11th, you'll see me going through this. You might need to hurry through it.